Astronomers discover gigantic spinning filament. Astronomers discover one of the largest spinning structures in the universe, a clue to how the Milky Way was born. Astronomers have uncovered one of the largest known spinning structures in the universe, a colossal rotating filament of gas, dark matter, and galaxies that may finally shed light on how the Milky Way and similar galaxies were formed. Now let's explore the deeper layers of this story here on the AI podcast.
Okay, so let's dive right in. We often talk about structure and, motion in space,
Right.
but it's rare that a discovery comes along that really just fundamentally alters how we think about cosmic mechanics, especially at the largest scales.
Exactly. And that's our mission for this deep dive. We're focusing on the identification of one of the largest rotating structures ever seen, a gigantic cosmic filament.
And this isn't just about finding something big. The real significance here, what makes this so profound, is that it might finally answer a question that's been nagging astronomers for decades.
A huge question.
Yeah.
How did massive galaxies, galaxies like our own Milky Way, get their spin in the first place? Billions of years ago. This might be the answer.
So the research we're looking at describes this colossal thread of galaxies, and it's spinning like a cosmic rolling pin.
That's a great way to put it. It's this vast line of galaxies, all embedded in gas and dark matter, and it's all rotating together.
And just to give you a sense of the scale right from the start, we're talking about a structure that contains more than 280 individual massive galaxies, all moving in sync.
Yes. And synchronized motion on that scale, that's more than just gravity. It tells you something fundamental about the architecture of the early universe. This is a game changer.
Okay, so let's try to define this cosmic rolling pin, because the scale and the geometry of it are just mind-blowing.
It is. So where to start?
The length?
The length, okay. This structure spans nearly 50 million light years across space,
50 million.
which puts it right up there with the largest structures we've ever cataloged.
50 million light years is a distance that's almost impossible to really visualize, but here's where it gets really strange. The thickness.
Yes.
You'd expect something that long to be, I don't know, bloated or thick, but it's not.
It's the complete opposite. It is shockingly narrow. For all that length, it's only about 163,000 light years thick.
The ratio is just incredible.
It is. And Professor Matt Jarvis had this perfect analogy to help picture it.
Right.
He said if you were to shrink that entire 50 million light year filament down to the size of a household rolling pin,
Okay.
it would only be a few millimeters wide.
Oh, it's an impossibly long, thin thread stretched across the entire cosmos.
Precisely. And that incredibly delicate structure is what's spinning. The whole thing, with all those hundreds of galaxies, is rotating at more than 246,000 miles per hour.
Wow.
That's about 396,000 kilometers per hour.
246,000 miles per hour for a structure 50 million light years across. I mean, usually when we talk about speeds like that, we're talking about, what, a spinning black hole? Or maybe a dense galaxy?
Exactly, a compact object. For a structure this immense and this relatively low density, to be moving with that kind of synchronized momentum,
It's unheard of.
it's truly exceptional. We've seen hints of this in simulations, but to observe it directly, that was the real challenge.
Which brings us to the smoking gun. How do you even prove something that massive is spinning? It sounds almost impossible.
It's an incredible technical challenge. So the researchers, in their study in the monthly notices of the Royal Astronomical Society, they zoomed in on a smaller section,
Okay, a more manageable piece.
a piece about 5.5 million light years long. And they focused on that bit because it had 14 very specific key galaxies inside it.
And what was special about these 14?
They were extremely rich in neutral hydrogen gas.
Ah, okay. And the hydrogen is the key. Because normally you're just looking at starlight, which only gives you 2D data, right? Like, is it moving toward us or away from us?
Exactly. But neutral hydrogen, it emits radio waves at a very specific wavelength. And that wavelength is highly susceptible to the Doppler effect.
So the movement of the gas changes the wavelength.
Right. The speed and direction cause a slight shift. A red shift if it's moving away from you, a blue shift if it's moving towards you.
So by tracking the hydrogen, they weren't just watching a few points of starlight. They were actually mapping the movement of the filament's fuel in 3 dimensions.
You've got it. And that 3D map gave them the absolute proof of rotation.
What did it show?
It showed the galaxies on opposite sides of the filament's central axis were systematically moving in opposite directions.
One side coming toward us, the other moving away.
Precisely. That differential motion is the unmistakable fingerprint of rotation. There's no other way to explain it.
But then it gets even stranger because it's not just the whole structure, it's what's happening inside.
This is where it gets really profound. They discovered that many of the individual galaxies inside the filament
Yeah.
are spinning in the same direction as the whole structure.
So they're all aligned. The little spins match the big spin.
It's a synchronized dance on a cosmic scale. And that kind of alignment is extremely rare.
I'm trying to picture that. Dr. Lila Young had an analogy for this, didn't she?
She did, and it's a great one. She said, to picture the teacups ride at a theme park.
Okay, I'm with you.
Each galaxy is a spinning teacup. That's you, spinning around. But the whole platform you're on, the cosmic filament, is also rotating.
Ah, that makes perfect sense. It's a nested rotation. It forces you to think about gravity acting on the entire system, not just the individual pieces.
And that's the key takeaway. That coordinated spin is the first direct evidence that these large-scale cosmic structures can actually impart spin to the galaxies that form inside them.
So the environment dictates the motion.
It seeds the rotation. The macro is directly influencing the micro.
So let's zoom out a bit. Cosmic filaments themselves aren't new, right? They're a known part of what astronomers call the cosmic web.
Right. The cosmic web is the fundamental large-scale structure of the universe. If you could zoom out far enough, you'd see matter isn't spread out evenly.
It's all clumped together.
It forms this vast, sort of sponge-like network. You have huge empty voids, and separating them are these immense sheets and walls of matter.
And the filaments are the threads connecting everything.
They're the threads. They are literally the cosmic highways that channel gas, dark matter, and whole galaxies from one massive cluster to the next. They control the fuel flow for galaxy growth.
Okay, so we know these highways exist. But what makes this one so special? What are the factors that make it a breakthrough?
It's the combination of four things, all found in one place.
Right.
First, as we said, the extreme shape, 50 million light years long but incredibly thin.
Right.
Second, the clear, measurable rotation of the whole thing at 246,000 miles per hour.
Okay.
Third, the alignment. The galaxies inside are spinning with the filament. And fourth, and this is critical, it's what researchers call dynamically cold.
Dynamically cold, what does that mean? Quiet, undisturbed.
Exactly. It means the galaxies and the gas inside haven't been through violent mergers or collisions. If it were dynamically hot, the whole structure would be a chaotic mess. The spins would be random.
But it's not, it's pristine.
It's pristine. And that coherence is what proves it hasn't been disturbed. It's giving us a clean look at how the universe worked a long time ago.
So it's basically a time capsule.
It's a fossil record of the early universe.
And the researchers seem to agree on that. They note that the filament seems young and largely undisturbed, which means we're seeing processes from the very first stages of galaxy formation.
And again, the key to that conclusion is the hydrogen. The galaxies are full of it.
The raw fuel for making stars.
Exactly. If this structure were old and had been through a lot, that gas would be gone. It would have been used up in star formation or blown out by supernovae. The fact that it's still there means we're looking at an early stage of evolution.
Which makes it the perfect fossil record to study these cosmic flows.
Dr. Madalena Tudoruk called it that exactly. A fossil record of cosmic flows. Hydrogen gas is easily influenced by motion, so these galaxies are perfect tracers for mapping the currents of deep space.
And this is where it really connects back to us, to our own home, because these flows are the same kind of flows that would have fed a young Milky Way.
Yes. This is how our galaxy got the raw material it needed to grow. By studying the mechanics here, we can finally understand how our own galaxy got its spin and accumulated its mass.
So it's the missing link.
It helps solve that puzzle of why so many galaxies spin the way they do. The filament itself is spinning, and it gives that initial rotational kick to the galaxies forming inside.
As Professor Jarvis said, understanding how cosmic structures form and evolve gives us the pieces we need to understand how galaxies like the Milky Way came to be.
And this is a very, very big piece of that puzzle.
Okay, so to sum this all up, we have this needle-thin structure, 50 million light years long, spinning as one coherent piece at over 246,000 miles per hour.
A structure that's dynamically cold and full of hydrogen gas.
Which makes it a fossil record, one that proves that the cosmic web itself can impart spin onto the galaxies within it.
Giving us a window into how our own Milky Way probably started its rotation billions of years ago.
An incredible discovery. But connecting this to the bigger picture, it raises a new question, doesn't it?
It always does.
If these cosmic highways are the architects of galactic spin, what else are they influencing?
That's the provocative thought. If these rotating filaments are out there, what about even larger structures? Are there super filaments that we can't detect yet? Structures that might be influencing not just the spin, but the entire future trajectory of the Milky Way, its path, its potential mergers.
So we understand the spin mechanism now.
But charting the full influence of the cosmic web on our ultimate fate, that remains the next great cosmic puzzle to solve.
Okay, one question for you. What is the newly discovered cosmic filament and why is it considered one of the largest spinning structures in the universe? Don't forget to comment it. Thanks.